Hi everyone, in this video we're going to go through the solutions to the probability SAC from 2018. I don't think the date's on there. Oh, there we go, 2018. So this is a 2-hour SAC and I'm not going to do every question, so I'm actually going to be a little bit sneaky and just refer to Mr. Chalker's working out. Okay, so just to save a little bit of time with the video. But I'll still talk about each question. So question 1, we've got the probability of A, probability of B, and the probability of A or B. Determine whether A and B are independent. So you should have in your bound reference formula sheet, or be familiar with the formula sheet. You do get the formula sheet on your exams and you're given it in your first SAC. Now for independent events, let me just go back to for independent events, the probability of A and B must equal the probability of A times the probability of B. All right, so for this first one, we've used the addition rule, but it's not in the form it's usually in. So if I just go back to the formula sheet and you can see the addition rule there, let me just turn the auto save off and also get my highlighter. All right, so this is your addition rule. So basically all they've done is switch these two around. So you can, because it is an equation, you can switch it around like that. And that's a terrible highlighter, we can hardly see it. So I'll just show you that we want the probability of A and B. We are given the probability of A or B. So we can just switch them around. Let me go back to, so because they're equal, they're independent. All right, moving on to question B. If the probability of A or B is equal to 0.85 and probability of B is equal to 0.63 and A or B are mutually exclusive, find the probability of A and B. Now, when they're mutually exclusive, and I can draw in here, but I can only do one color. When they're mutually exclusive, what they have in common is 0. So when you think about your Venn diagram, the two circles don't overlap. So there's A and there's B. Mutually exclusive events are not the same as independent events. All right. So you can see we've got the two-way table here. I'll just draw the other line so we don't get mixed up with all these numbers. All right, so you put 0 here. What else have we got? The probability of B is 0.63. So that means the probability of B and not A is also 0.63. And then you can just work your way down because you know that should be 1. So 0.63 and 0.37 add up to 1. Now the other tricky thing is if you did that, so we've only got the first row and this last column, and we don't have, if you're wondering where the 0.22 and the 0.15 come from, now this 0.15, if we consider the probability of A or B is 0.85, then the probability of not A and B is 0.15. Right, so that's where the 0.15 has come from. So that means the probability of A is 0.22 because I have to add up to 0.37 and then you just can complete it there. So the trick was, I guess, identifying that 0, knowing it has to all add up to 1 and that 0.15. All right, so there's your probability of A. I always like drawing two-way tables, more than Venn diagrams. Okay, so the exact value of the probability of A given not B. Okay, so you do need to use the conditional probability formula. So if I just go back to our formula sheet, here's our conditional probability formula here. Okay, so the probability of A given B, just make sure you have everything in the right order. So your condition always goes on the denominator. All right, so scrolling down. All right, question 2. The probability of a netballer scoring a goal is 0.8. Find the probability that out of 6 attempts a netballer scores a goal. Okay, so this question here doesn't say that it's binomial distribution, and this is where students do have a bit of trouble thinking about, well, how do I do this? Now, it's always a good tip to look, something to look out for is whether you've got a probability of success and a probability of failure. So you've only got 2 possible outcomes, success and failure. So for this question, the probability of success is her scoring a goal. So her failure would be not scoring a goal. They're the only 2 possible outcomes. All right. And she's got 6 attempts. So you can see there n equals 6 and p equals 0.8. Now we can just straight away use the binomial theorem, so binomial distribution, sorry. So you can see we want 4 times, so x equals 4. There's just the notation. So you can see Mr. Chalker has used 6c4, but that's the same as if you wrote 6-4. It's okay. 0.8 to the power of 4 and 0.2 to the power of 2. So remember, this is Q. So Q is your probability of failure. So just 0.2 because 0.8 and 0.2 have to add up to 1, or P plus Q have to add up to 1. And then you can just do that on your calculator. You can also just do it using the function in your calculator. Just notice though, it is worth 2 marks, so it's probably worth just identifying N and P. Don't just go straight ahead and write the answer. All right, even writing the binomial distribution would be good. Doesn't take you long to do. All right, question B, 4 times given that she scores at least 1 goal. All right, so with a binomial distribution, it is important that you get your inequality correct. So at least 1 goal, so your lower bound is 1, and your upper bound, how many goals is she doing? 6. So when you put it into your calculator, just writing down the lower and upper will mean you won't accidentally put in a value or the incorrect value, especially if it was more than 1 goal. That would mean it would change your inequality sign to just greater than, and your lower limit would then be 2. Okay, so just be careful with that sort of language. All right, moving on to question 3. So the height of plants sold by a garden nursery supplier are normally distributed with a mean of 20 and a standard deviation of 5. Complete the following table by finding the proportions for each of the 3 sizes correct to 4 decimal places. Okay, so we've got our mean, our standard deviation. All right, so remember in your calculator, it always does the standard deviation first. So if it helps you just not make that small error of getting your mean and standard deviation around the wrong way, just write your standard deviation first and then your mean. What I actually mean by that is if I just quickly get the calculator up and we're going to choose normal, see how your standard deviation is first and then your mean. And often you see questions where it's got the mean written first and then the standard deviation. So you do just want to make sure you don't get them mixed up. So maybe writing them down will mean you won't get them mixed up. All right, so with your normal distribution on your calculator, let me just get it back up. All right, so for the first one, you can't see the top of my calculator, so let me just scroll down. So less than 10. All right, so we can't have negative plants, but I'm also just thinking, yeah, you'd probably be fine with just doing 0 because 0 is 4 standard deviations from the mean. But you could also use infinity. I don't think it would be much difference, but yeah, let's stick with 0. Your upper bound is 10, so we're less than 10. Now with your normal distribution, less than 10 also includes 10. All right, so your standard deviation is 5, and then your mean is 20. All right, so you can actually see I got 227.02271. Now I wonder if, let me just think actually, whether I should have done infinity. Let me just negative infinity. I don't know whether you can hear, but my dog is scratching away behind me. All right, the upper bound is 10. Maybe if we wrote 9, let's just check. All right, yeah. So you can see the difference there. Probably should have used negative infinity, but it does make sense that you can't have negative number of plants. But yeah, when you are using the normal distribution, you should really use negative infinity as your lower limit, unless it's been specified like in for the medium or infinity. So when you do large, you would go from 30 to infinity. All right, so just make sure you use infinity and negative infinity for the normal distribution. All right, question B, find the expected cost to the nearest dollar for 100 plants chosen at random from the garden nursery supplier. All right, so we've got our probabilities here. So for the small, it costs $1.50 times your probability. The medium, $2.50 times your probability, and 4 times your probability. Now, I wouldn't use those rounded values in an exam situation. Okay, but if you do it in your SAC, that's fine. I won't penalize you, but don't use the rounded answer. I would just scroll and use that. Although sometimes when it says rounding to 4 decimal places, it's fine to reuse that value. Okay, so once you've got that cost, because we're looking at 100 plants, we're multiplying that by 100. So the expected cost would be $251.14. So just remember, you do need, when we're working with money, you do need to round to 2 decimal places. Now, I know when you pay cash, it is rounded to the nearest 5, multiple of 5. But always assume with any financial questions or money questions, just pretend you're paying by debit card, and debit card, it doesn't round to the nearest 5. All right, very thirsty. Just having a drink. Okay, question 4. The number of customers X waiting to be served in a florist shop at 6 p.m. has a probability distribution given. Okay, so we've got 0, 1, 2, 3. So that's the people waiting and the probabilities. So with the probabilities, you can see you've got K. So you know that K is going to you're going to have to find K. All right. When you do that, all your probabilities add up to 1. Okay, so all of these, all right, sum to 1. So you can see here for question A part 1, show that K equals 1 by creating, so that K equals 1 is this K, all right, and this K, and this K, and this K. It has nothing to do with the fact that it sums to 1. It's just coincidental, all right? So K is equal to 1 by creating and solving a quadratic equation in terms of K. So you can see here we've added them all up, all right, and there's a common denominator of 9, so that's why it's all put on over 9. And then just solving by hand, an easy quadratic to do. Looks like 2 has been taken out as a common factor. And then you can divide both sides by 2 to get rid of that. And then you got K plus 5, K minus 1. Now that means K is equal to negative 5 and K is equal to 1. Now, you should always consider multiple solutions. Okay, so here we've got k equals -5, k equals 1. Now we know k equals 1, but we should actually think about, well, why is that true? So if I was to put -5 into these probabilities, so every single one except for 0, the first one, you're going to have negative probabilities. So remember, your probability has to be between 0 and 1. So that's why k has to equal 1. Because if we substituted k equals -5, let's say for 3, we're going to have -5 on 9, and we can't have a negative probability. It has to be between 0 and 1. All right, hence complete the following. So that's just substituting k in. Calculate the expected value. So when we've got discrete random variables, it's just your value of x times your probability. Okay, so you can see the working done for you there. All right, so 0 times 1/9, blah, 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 and you get 13 on 9. Remember to do your exact value unless it specifies decimal places. So you can just leave it as 13 on 9. Don't go ahead and write it as a mixed number fraction. Okay, you don't have to. Just leave it as a mixed, not a mixed number, a improper fraction. Yeah, and if it's, just leave it as its simplified form as well. Don't write, 26/18. You should be simplifying your fractions. All right, calculate ex squared. So we've done that before. So just your value of x we squared. And we do that to find the standard deviation. So your standard deviation, remember, is the square root of your variance. Oops. And your variance is equal to ex, oops, got my squared, minus the mean squared. I'm running out of room. All right, so that's your formula for the variance for discrete random variables, and your standard deviation is the square root of that. But all of that should be in your bound reference. Okay, you can see that we've simplified this third as well. So when you take the square root, of the numerator and the denominator. Just wondering whether square root of 56 can be simplified. Yeah, it can. So that could actually be simplified further. But the important thing to note is leave it as an exact value. Okay, even if you just leave it as an unsimplified third. All right, calculate the probability that the number of customers waiting to be served in the florist shop at 6 p.m. each day is no more than 2. Sorry, I feel like I just read that incorrectly. All right, so we want the probability that x is less than or equal to 2, so no more than 2. So we want 0. So this is no more than 2 is 0, 1, and 2. So if I go back up here, we can add 0, 1, and 2, or you can just do 1 minus what we don't want, which is 1/9, and you can get the 8/9 doing it that way. All right, question 5. The continuous random variable x has probability density function f given by, okay, so we've got our hybrid function there, sketch the graph. So just remember when you've got it, when you sketch it, I remember when I did this question, sometimes I didn't do the 0, always include the 0, and also think about your inequality sign. Sorry, Lucy's just shaking in the background. All right, so when you've got, so this one here, we've got greater than or equal to, so it's a solid circle. And when it's not equal to, so this is just x is less than 0, you have to have an open circle. So just remember that. So when it's included, solid circle, not included, open circle. Okay, sorry. And you can easily graph e to the negative x on your calculator. All right, find using calculus the probability that x is less than 0.5. Okay, so we're just setting up the definite integral. Okay, so we've got 0.5 here. If you want to write it as a half, that's fine. You know, I prefer fractions. So we're just doing the definite integral. You need to know the antiderivative of e to the negative x. So hopefully you've got all your calculus stuff or your antiderivatives in your bound reference. And yeah, just doing the substitution. Anything to the power of 0 is 1. So e to the power of 0, that's where the 1 has come from. And then you've just switched sides with those terms. All right, x is greater than or equal to 1. All right, so obviously missing a little bit of working out there. Or actually, let me just, what are we going to? X is greater than 0. You could just also do 1 minus x equals 0. And then D, we've got a conditional probability. So x is greater than or equal to 1, given that x is greater than 0.5. So you're given those, or you calculated those two previously, and you just need to do that. Remember, you do have your calculator on you. So if you're expected to show working out, you can use the calculator to aid your steps. So let's say you had e to the negative 1 over e to the negative a half, and you're like, oh my God, how do I even do that? Just do it on your calculator and then write the answer. All right, just remember you should be switching to standard, all right, not having it in decimal. Unless you want a decimal answer, have it in standard and always keep it in radian, okay? All right, pushing on. All right, question 7. Actually, question 6. Is that a bit tricky? Where is 6? 6 is missing. I wrote down 6 as a tricky one. So let's go to the other document. It must be on here. Maybe Mr. Chalker found it hard to and just didn't do it. I don't think so. All right. So question 6, Vanessa Smith is a contestant in the jumping event at the Asian Championships. On a particular day, Vanessa jumps X meters. X is a normally distributed random variable with a mean of 7.2 and a standard deviation of 0.2. Find the probability that Vanessa jumps more than 7.5 meters. Okay, so let's write out what we have. So it is a normal distribution, so I probably should have highlighted that. Usually if it's a normal distribution, it says it's normal. If it says it's standard normal, remember that means your mean is 0 and your standard deviation is 1, but this is just a normal distribution. All right, I'm going to write standard deviation first because that's how we're going to put it into our calculator. And then our mean, 7.2. All right, so we want to find the probability she jumps more than 7.5 meters. So the lower limit is 7.5 and the upper limit is infinity. Wouldn't that be funny? Like she jumps and she ends up in space. Okay. Where is my calculator? There you are. Okay, so interactive distribution, continuous, normal CDF. All right, so her lower bound is 7.5 and then the upper bound is infinity. She can jump into space. Standard deviation is 0.2 and your mean is 7.2. All right, so what have we got? 0.668. All right, during the championships, each competitor in the long jump event has 5 jumps. In her 5 jumps, find the probability that Vanessa's first 3 jumps are all less than 7.5 meters and both her last 2 jumps are more than 7.5 meters. Okay, so we want to find the probability. Okay, so let's just say, how can we use this as notation? So less than, so, oh, I don't know how to, let's just do less, and her last two jumps are more. So more. All right, so we need it in that order. So less, more. Now, we know that the probability that she is great, more than 7.5 is 0.0668. So let's just get back on the calculator. Oh, where's my calculator? You're right down there. All right. So this time we're going to do the other way. So the lower limit now is negative infinity. So this time she is jumping into the ground. 7.5. Standard deviation is 0.2. And our upper limit, oops, no, sorry, I was reading the wrong thing. Our mean is 7.2. All right, so we've got 0.9332. All right, so I'm just going to write that here. So 9332. And you'll notice that they do add up to 1. All right, so you could have just done 1 minus that. Okay, so we want the probability that she is less than 7.5 3 times. So we could multiply them by themselves 3 times. So it's not 0.9332 times 3. Okay, so don't make that mistake. You're actually multiplying it by 0.9332 3 times. And then you're multiplying it by the other one, 0.0668 times 0.0668. Now, you didn't have to do that long way. I just wanted to show you that. So you could have just done 0.9332 to the power of 3 times 0.0668 to the power of 2. All right, so let's get our calculator. Now, I'm not going to use a rounded value, so I'm just going to highlight that. Then do to the power. Where are you, power? Oh, you're down here. To the power of 3, and then times. And I'm going to highlight this one. Go down to the power of 2. And of course, you're going to do that, aren't you? Let's just change it to decimal. Come on. Let me try again. There we go. All right, so remember that E, don't be scared of it. It just means we need to replace that E with times 10. So I'm going to write down 4 numbers. So 3627 times 10 to the negative 3. Was it? I can't remember. Negative 3. All right, so you can leave it like that. Probably not good to leave it with scientific notation. So the negative 3 just means we move our decimal spot 3 places. So you can write 3627 and then just add your zeros in. So we've got 1, 2, 3, and there it is. So that's not 4 decimal places. So let's just write it now to 4 decimal places. All right, part 2, at least 3 of her jumps are more than 7.5 meters. All right, so this is where it might be a little bit tricky because we're now introducing the binomial distribution. Now, there are 2 outcomes. The probability of success is that she's jumping more than 7.5 meters. So we worked that out to be 0.0668. And the number of trials, so she's doing 5 jumps. and we want to find the probability at least 3. So x has to be greater than or equal to 3. So if you want to, you can write down your lower and your upper just so you don't get them mixed up. So we want to be greater than or equal to 3. So we're at 3 and 5. All right, I'm just going to go back up. Okay. Sorry, I was just thinking about whether it was right from the start, but it looks good. Okay, so we don't want discrete. Okay, so this time we're looking at not the probability of her jumps, but her number of jumps. So we want binomial CDF. So the lower limit is 3. The upper limit is 5 because, oops, not 4, because she's only doing 5 jumps. All right, she can't do infinity jumps. The number of trials is 5, and the probability of success, well, I should really highlight this. So let's go back. Sorry. I'm going to highlight that. Copy. All right, let's go back and do it again. All right, so, oh my gosh, I don't think you can hear my son, but he's getting a little bit too excited on that PlayStation. All right, so just make sure it's written correctly. Cool. So 3, 5, 5. All right, so the, no, I've made a mistake somewhere there. No, I haven't made a mistake. I read that as 2.69 and I was like, why is it more than 1? And then I saw the E on the end. All right, so we've got 2.69 times 10 to the negative 3. All right, so I could put it to more decimal places. There's a 0 there, and when I round, it's not going to make any difference. So, all right, so I'm going to write 269, move your decimal place 3 spots. So 1, 2, 3. So 1, 2, 3, here it is. And if we're doing that to 4 decimal places, we've got 0.0027. So, yeah. All right, so for question C, 75% of Vanessa's jumps are greater than A meters. What is the value of A? All right, so we're now doing the probability that X is greater than A is equal to 75%. So as a decimal, that's 0.75. So we do need to also use the, so we're using the inverse normal. So we do need to have the standard deviation and the mean. All right, so that was given to you at the start of the question. All right, so interactive distribution, inverse normal. We want to be 75% are greater, so we want to go to the right. All right, so the probability is 0.75. The standard deviation is 0.2. And the mean is 7.2. Okay, so the value of A is 7 point, and we should just probably do it to 1 decimal place. I'm just doing 1 decimal place because the mean is to 1 decimal place. Now, if you think about the normal distribution, which I probably should have drawn at the start, and I keep going back to the start to think about whether my answers actually match the normal distribution. So let's quickly draw it. So here we've got 7.2, and if I go 3 standard deviations either side, So we're going up by 0.2 each time. So 7.4, 7.6, 7.8. And then down the other way, we're going to have 7, 6.8, and 6.6. So if we wanted to have 75%, remember if I was to split that in half, then this would be 50%. So you would obviously expect something below 7.2. Now, if I was to include this section here, see how it's quite a large area? All right, so it's just because it's looks halfway, it's not halfway. All right, it's not half there because you have, all right, so using this, if you think back to 16b, chapter 16b or section 16b, one standard deviation either side of the mean is 68%. So this is 34%. So 7, a score greater than 7 would be 84%. So yeah, 75% for 7.1 does make sense. So having an understanding of the percentages does help you think about the real, how real your answer is. That's why when I was doing this one here with 0.68, 7.5 meters is in between 7.4 and 7.6. So we're kind of just looking at this area here. And where am I? All right, so it kind of does make sense that it would be 0.0668 because if I was to do it as a percentage, that would be around 6%. All right, let's move on because I'm getting sidetracked here. During training for the championships, Vanessa had 60 practice jumps. How many of these jumps would be expected to be more than 7.5 meters? All right, so the probability of being more than 7.5 meters, remember we did that on our calculator. I'll just get my calculator back up and scroll up. So it's here. I think I've probably still got it copied, but I'm going to copy it again. And then we're going to paste it. All right, so if she's got 60 jumps, that is just the probability that she would get greater than 7.5. So we're just going to multiply that by 60. So 4 jumps. All right, so 4 of those jumps you would expect to be more than 7.5 meters. All right, after her 5 World Championship jumps, Vanessa's best jump was 7.8 meters. She was leading the event with Wilma. Oh my God, Wilma. From the Flintstones' best final jump still to come. In a particular jump, Wilma jumps Y meters, where Y is a normally distributed random variable with a variance of 0.16. All right, we've got a bit of information here. Let's highlight. So Vanessa's best jump, 7.8. And we're going to use Y to represent Wilma's normal distribution. So we've got a variance of 0.16. If the probability that Wilma's jump is more than 7.8 meters is 0.21, find the mean of the distances that Wilma jumps, correct to 2 decimal places. All right, so let's just think about this. I don't think that first sentence plays any role in the working out. It's probably just to compare Wilma to Vanessa. Now, when I say this variance, I know that the variance is equal to standard deviation squared. So that means, therefore, your standard deviation is the square root of your variance. So in this case, it's going to be the square root of 0.16, which is equal to 0. Just wondering if it's point. I think it's just 0.4. Let me just double check that I'm thinking about whether my decimal places are correct. Yep. All right. Now, what else have we got? If the probability that her final jump is more than 7.8, so the probability that y is greater than or equal to 7.8 is equal to 0.21. Find the mean of the distances that Wilma jumps. Correct to 2 decimal places. Okay, so we want to find the mean. Now the mean is not the same as Vanessa. All right, so we need to just use the understanding of the standard normal distribution. So if we're looking at the probability that y is greater than 7.8, that means the probability of z is greater than 7.8 is equal to x minus the mean over the standard deviation. Now, what we need to do is just find out what this x is. Okay, so what I need to do on my calculator, if I just get it up, where are you? All right, so if we go to inverse, normal CDF. All right, so we're looking at greater than 7.8, so we're going to the right, and we know it has to be 0.21. So basically all we're doing here is looking at what value, all right, is going to give us 0.21 on the standard normal distribution. Okay, so I get 0.806. So if you think about your normal distribution, we've got a mean here, and we know the standard deviation. Okay, so we can go 1, 2, 3 either side. But what we need to do is, well, if I change it to the standard normal distribution, that can help me relate the normal distribution to the standard normal distribution. All right, so we only want to look at the top 21%. Okay, so I'm not too sure where that is. Let me just think. Anyway, I can't think off the top of my head, so we'll just say it's around here. Actually, I know what it is because I just did it on the calculator. It's on just the other side of 1. All right, so that probability there is what we're going to look for using the standard normal, so these green values. So don't worry too much at the moment about the mean, okay, because we can deal with the standard normal distribution. Okay, so if I get my calculator back up, that's what we just did. Okay, so we use the inverse normal, we use the standard, so we've got a standard deviation of 1 and a mean of 0, and we're using 0.21. So what is that? 0.806. So this value here is 0.806. So what I'm going to put in here, all right, and I just realized this should be a y. So we want 7.8 minus the mean, which is what we're solving for, over your standard deviation, which is 0.4, and that is equal to your z-score, which is 0.806. Now you can just go ahead and solve that. So if I was doing that by hand, we've got 7.8 minus your mean is equal to 0.806 times 0.4, and then your mean is equal to 7.8 minus 0.806 times 0.4. So if I just quickly do that on the calculator, if I can find it, All right, so 7.8 minus, and remember to just drag it down, times 0.4. All right, and we get 7.477. Now, I don't know how many decimal places it, 2 decimal places. Okay, so we're going to have 7.48. All right, so I just realized question 6 is question 7 on the solutions. There you go. So yeah, we've gone through that already. I'm just, when I look through the answers, the number of decimal places was a bit different. Just remember with your exam, it will always say, so don't think you need to check. All right, I don't know why question 8 was crossed off. Is it in the actual SAC? Or maybe decided later not to do it. All right, so let's move. Oh, no, it's a different question 8. All right, let's go back to the SAC. All right, I know there's questions there. We can see them. I'm just going to skip. Sorry, I'm already over 40 minutes, I think. Okay, so let's just make sure these questions match up. Cool. All right, so question 9. Oops. So suppose that the proportion of people in a certain country who with a certain attribute is 0.25. If a random sample of size 8 is selected from this population, find correct 2, 3 decimal places. Girls, this is sampling, which we haven't actually done. So I might actually skip that. I was wondering if anyone highlighted that as a difficult question. No. All right, so I just noticed that the students who did want some help with this didn't actually write question 9, although I guess it's question 8, isn't it, on this one? All right, so I'm going to skip this because sample size sampling isn't on your SAC. It would be good to revisit this prior to your exam. So I'm going to skip this, and I apologize for doing so. It probably would still make sense to you because sampling is not overly difficult. All right, let's have a look and see if this one's okay. All right, I won't know until I start reading it. So question 10, a study of a large number of adults finds that their resting heart rate, x beats per minute, is normally distributed such that n 68.25. So it's told you that it's a mean of 68 and a variance of 25. Remember the standard deviation. So if you wanted to quickly write that down, is just the square root of your variance, which is 5. All right, find the probability that a randomly selected person from this group will have a heart rate between 58 and 78 and less than 63. So it has said it's normally distributed, so you can just easily do that on your calculator. All right, so I'm not going to do that because we've done heaps of normal distribution and it's not too tricky. Hopefully you get the right answer though, the answers are there. Find K such that 16% of heart rates are greater than K. So this is where we got to use the inverse normal. So we use the same standard deviation and mean, but we're using inverse normal this time. So I might do this question, part B. All right, so just get my calculator up. All right, so interactive, normal, inverse, distributions, inverse, normal. We want greater than K, so 16%. When we're doing greater than, it has to be to the right. If it helps, you can do it through the statistics menu, or you can draw a rough sketch to know whether you're working from the left to the right. So we've got 0.16, our standard deviation is 5, and our mean is 68. All right, so there you can see 72.97 is your value of K. All right, question C, given that when the variable is converted to a standard normal variable, Z is greater than, the probability that Z is greater than A is 0.3. Oh, excuse me. Find the probability of Z is greater than negative a. So this is just understanding the relationship, the symmetrical relationship of a normal distribution. So if I know there's already a normal there, but I'm going to draw my own. All right, now the Z just means we've standardized it, and it's, you can see the word standard there. So we've got a mean of 0 right in the middle, and Z is greater than A. So A, we don't know where it is, we can just say it's there. All right, so this area in here is 0.3. Now, because normal distributions are symmetrical, we can have on this side negative A. So this is also 0.3. And then you can play around with the different probabilities as well. So if we want Z is greater than negative A, we're actually looking at this area in the middle and this area down the end. And when you think you've got 0.3 either side and they have to add up to 1, so this area must be 0.4. So that's where the 0.7 has come from. So you can either do 0.4 plus 0.3 or 1 minus what you don't want, which is 0.3. The probability that Z is less than negative A, you can see there is 0.3, and the probability that Z is less than A is 0.7. So it's just using the symmetry of the normal distribution. Question D, find the probability that a randomly selected person from this group will have a heart rate greater than 78, given that it is greater than 73. So the word given that means it's a conditional probability question. All right, so make sure you write the correct notation. On our formula sheet, we should have, yep, oh yeah, we've already looked at that. So there's your, oh, it's getting cranky with me. Well, that was your conditional probability formula. All right, where are we? Let's go back to the SAC. Oops, no, we're going to this one. Okay, so there's your conditional probability, which you should be able to do. Okay, so we've done normal distribution. We just want x is greater than 78, so it's 78 to infinity, and then greater than or equal to 73, it's 73 to infinity, and just using a same mean and standard deviation given to you in the question. I just realized why there's a blank. It's because he probably printed one-sided. There we go. All right, question 11. Oh, I love these types of questions because they're symmetrical. And there's been some on past exams, so they're really great. All right, a random variable x has a probability density function given by. So what, and I think I've I have done a question like this. Okay, so we've got two linear functions. I know they're linear because the power of x is 1. Okay, now when you're drawing them, okay, so part A, first of all, you have to calculate k. So remember that, they've used the area of a triangle formula. So they've kind of, I guess, worked backwards. So if you sketched it, you would know it was a triangle, or you could just do a definite integral. All right, so yeah, that's where that has come from. So just using half base times height. So your base is from -2 to 2, and your height is 2k. And you can find that because that's your y-intercept. So you let x equal 0 and you get 2k. So that's what that formula is, the area of a triangle. But you could also just do your definite integral. You do have 2 here. I think sketching it first is better because then you can see that they're symmetrical. But when you're given multiple ones like this, do just think, oh, they're probably symmetrical. So the area under this curve is 1. So you could also use a definite integral either for the whole thing. So you'd then have to use 2, or you can just go from 0 to 2. So with your definite integral, 0 to 2, and we're doing k 2 minus x dx is equal to, we only want half of it, so it's got to be equal to a half. All right, so because it's symmetrical, you don't have to do both. All right, so k is equal to a half. When you're sketching it, that's what it looks like. Probably don't leave it as 2k up there. You should probably say what that y-intercept is. Okay, moving on to question C. Find the probability that we're between -1 and 0.5. So you do have two separate functions. So what Mr. Chalker has done is done the whole area of the triangle is 1 and then done the area of the two triangles on the end and subtracted them from 1. Or if you were doing a definite integral, which he hasn't done, you would have to do two separate ones. So I like the idea of using the area of a triangle, but you could also go from -2 to 0 with your first function, and then your second one, so whatever that is, I can't remember, doesn't matter, you know what it is. And then for the second one, we're going from 0 to 2, f of x dx. All right, and that'll give you the same answer. But the concept of taking away the two triangles from the larger area, which is 1, is pretty cool. I like that. All right, question 12. Sarah has a die which is loaded. What's it mean by loaded? Sounds like a gun. When the die is rolled, the probability of the uppermost face occurring is shown in the following table. So you've got 6 sides of the die. If P is 0.05, find the exact value of Q. So where is Q? Here's Q. All right, so you just need to substitute in a half for all of them. No, not a half. 0.05, so you can easily just do that on your calculator. Part B, on Monday, Sarah rolled the die twice. Find the probability that both scores were 6s. So to roll a 6, so if it helps, you can go ahead and just put the actual probabilities in there. We saw that Q is 0.25. So Q is representing the probability of a 6, so 0.25 squared. If you wanted to do that without a calculator, so 0.25 is a quarter, you're just squaring that. 1 squared is 1 and 4 squared is 16. This also gives you a terminating decimal. So when you have a terminating decimal, write all decimal places like you have here. Do not do any rounding. Find the probability that the total of the scores was 9. Okay, so 3. Just trying to figure out what that working is. All right, clearly getting late because I just misinterpreted what that question was asking. I thought the probability was 9, but the total of the scores is 9. So the different combinations you can have are 3, 9, 4, 5, 5, 4, and 6, 3. So what we have here, 3PQ, even on your calculator, you can define P and Q if it makes it easier. So I'm assuming the probability of getting a 3 is 3P, and the probability of getting a 6 I know is a Q. So you just multiply them together. So 3P times Q gives you 3PQ, 4 and 5, and so forth. Okay, so you get 7 over 40 or 0.175, which I think is also a terminating decimal. Find the probability that if the total was 9, that one of the scores was 6. So this is a, find the probability that if this total score was 9, then one of the scores was 6. So we want, it is conditional probability, so we want it to be a total of 9 and 1 is 6. Okay, so there's a probability for 1 is 6, that's the total of 9, which you worked out in the previous question. All right, and you get 3/7. Again, leave it as an exact value. I don't think this is a terminating decimal, but I don't know off the top of my head. All right, question C. On Tuesday, Sarah rolled the die 5 times. What is the probability that there are at least 2 scores of 2? All right, so the probability of getting a 2, so if we go back up to the table, 2p, so 2 times 0.05 is 0.1, All right, so this probability is 0.1. That's where the 0.1 has come from. So the probability of at least 2, so you can use the binomial distribution. So the 2 outcomes, so P being the probability of success, so the probability of getting a 2, and Q is the probability of getting anything else, which is going to be 0.9. All right, so X is greater than or equal to 2, so you just use your binomial distribution. We want the lower and the upper. All right, so at least 2, so we're including 2, and our upper limit, she's rolling it 5 times. All right, so you just put those values in, so NP, lower and upper. On Wednesday, Sarah rolled the die n times. Find the least value for n for which the probability of obtaining at least one score of 2 is more than 0.5. So we want at least 1, 2. So the probability that X is greater than 1. All right, so the 1 doesn't refer to what you roll on the dice. It's how many 2s you roll. Okay, and that has to be greater than 0.5. Now, basically, the probability that X is greater than or equal to 1 is the same as 1 minus the probability that X is equal to 0. So you can see that's why we've got X is equal to 0 there. And if now you switch the inequality sign, let me just think. All right, so what have we got? So we've got the probability that X is equal to 0, is 0.9 to the power of n. All right, I'm just going to do over the side here because we should write probability that 1 minus probability of X equals 0 is greater than 0.5. And if I was to subtract 1 from both sides, so that's going to leave me with negative probability that X is equal to 0 is greater than negative 0.5. And now if I multiply through by a negative, I do have to switch my inequality sign. So we're going to have the probability that X is equal to 0 is now less than 0.5. So that's why the inequality sign has switched direction. The probability that X equals 0. So that's not rolling a 0 on the die, that's getting 0 2s. All right, so we know the probability of getting a 2, so rolling a 2. Oops. Oh, can I get rid of that? Okay, rolling a 2 is 0.1. So not rolling a 2 is 0.9. So that's where the 0.9 has come from. And we want to know how many times we have to roll it. So it's to the power of 9. So how many times do we not roll a 2? Okay, so it's bites to the power of n. And then you're just solving for n. All right, so now we can just easily do this on the calculator, but to get rid of that 0.9, we just take log of base 0.9, and that gets rid of that. If I just go onto my calculator though, where are you? So I just did it. So you can see there log base 9 and your argument is 0.9 and 0.9. So we get 1. So that's why the 0.9 goes away. But then on the right hand side, we have log 0.9, 0.5 is 6.578, blah, blah, blah. So that's where the 6.6 has come from. Now you will notice that your inequality sign now changes direction because when your base is between 0 and 1, so here it is 0.9, it is a negative. But because 0.5 is also between 0 and 1, you've got a negative, and a negative makes that positive 6.6. But if you're ever unsure, you can just solve that inequality on your calculator. So if we just go to solve and we want 0.9 to the power of n is less than, so we'll get the less than sign up, 0.5. We want to solve for n. All right, so you can see there it has moved the inequality sign for you, so you can easily do that. Now, because we're looking at how many times we roll the die, so obviously we have to roll it a discrete number of times, so that's why it's 7. You do have to think about the situation. So 6.6 does round up to 7, but if I, let's say, had 6.2, I can't go and write 6 because you're looking for the least value, least number of times you can roll the dice. So if you round it down, you're going to have a probability that is below 0.5. So always think about the context before you round. Okay, so here it clearly makes sense to round up to 7 because 6.6 rounds up to 7. But if it was 6.1, you would also round up to 7 because if you rounded down to 6, your probability would no longer be 0.5. Okay, it would be less than 0.5 and we want it to be more than 0.5. All right, let's move on. All right, question 13. When Slow-Mo Inc. surveyed all its offices throughout the state, it was found that the time taken by employees to complete a task is a continuous random variable x with a probability density function, blah, 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 blah. Okay, so this time they're not linear and we still have 2. Okay, so find your expected value. So with continuous random variables, we do just put the x in front of the function, so you can see that there. And because we have 2 of them, we do it twice. So we go from 0 to 2 for the first, and then for the second one, we're going from 2 to 4. And then you can just do that on your calculator. All right, in a random sample of 200 Slow-Mo Inc. employees, how many members would be expected to take more than 3 minutes to complete the task? All right, so we've got x is greater than 3, so we're more than, so make sure you get, with continuous random variables, it doesn't matter with your inequality. So we're going from 3 to 4, let me just scroll back up. All right, so we do need to also think about which function to use. Because we want more than 3, that's why we use the second one. Okay, so we're going from 3 to 4. All right, so that's your expected value. That's your average, what you would expect on no, sorry, that's not your average. That's your probability. All right, so if we've got 200, okay, so you just multiply it by 200. If there was 1,000, you multiply it by 1,000. We get 52.34. Obviously, we can't have 0.34 of a person. So you would expect 52 employees. Because we're looking at probability as a continuous random variable, the rounding doesn't matter. Unless it was no, so we should more than, yeah. So roughly 52. So I think that's fine to round to 52. All right, question 14. So I think this is the last question. A manufacturer makes metal rods whose lengths are normally distributed with a mean of 140 and a standard deviation of 1.2. Find the probability that a random selected metal rod is longer than 141. Okay, so we've got normal distribution, we've got a mean, and we've got a standard deviation. So quite easy to do on the calculator. A rod has a size fault if its length is not within d centimeters either side of the mean. The probability of a rod having a size fault is 0.15, so that's our probability. Find the value of d correct to 1 decimal place. All right, so this question is quite similar to one of the previous ones we did, where we had to find the mean. This time we've got to find the standard, it's not really the standard deviation. So we're looking at d centimeters either side of the mean. Now, this diagram on the left side is probably where I want to start. So we know that 0.15 is if it's not within d centimeters of the mean, which is 140. So it needs to be between 140 plus d and 140 minus d. Now, the 0.15 is the probability of it having a fault. Now, because it's normally distributed, the 0.075 just comes from 0.15 divided by 2 because it is symmetrical. All right, so that's where the 0.075 has come from. Now, I prefer the red calculations here. I'm not too sure what he's done with the d over 1.2 because that's the standard deviation, and we don't know what the standard deviation is, do we? Oh, yes, we do. Oh, there it is. Okay, so use the standard, the Z value formula. But if I just go onto the calculator, if you're wondering where these values have come from, so I'm going to use inverse, and I'm going to do it with the standard. Sorry, I'm very tired and can't concentrate. So the standard normal distribution. Okay, so I'm just going to go to the right. So I'm going to look for this value 140 plus d. So the probability is 0.075, and I'm just going to use the standard normal distribution. So when I use the standard normal distribution, I get 1.4395, and you can see that's here. Actually, I don't know where he got the red. I thought I was going to do it the red way, but I'm doing it this way here. So basically, if we thought this was a standard normal, 140 is 0, and then here at 140 plus d is 1.4395. So that's our Z score. Now, if you think of your Z score formula, and I'm running out of room here, so Z is equal to X minus your mean over your standard deviation. So for this question here, we've got, all right, so Z is 1.4395. Your value of X is 140 plus D. And then we've got minus your mean, which is 140. Whoops. And then over your standard deviation, which is 1.2. So you can see the 140s cancel out there, and then we're left with D over 1.2 is equal to 1.4395. And that's where the 1.727 has come from. Now, the other method, I'm not too sure where that has come from, and I just don't have the brain capacity to really think about it too much at the moment. Maybe it is already multiplied by 1 point. No, I don't know. All right, question C. A random sample of 3 rods is taken from a crate containing a very large number of rods. Find the probability correct to 3 decimal places that the sample contains exactly 2 rods with a size fault. So this time, again, it's hard to see. It's not referring to binomial distribution, but when you start taking, when you start looking at probabilities where you've got a probability of success and a probability of failure, you can start thinking along the lines of binomial distribution. And if you're looking at a sample size of discrete number, so in this case we've got 3, or if you're doing a number of trials, or if you're shooting goals or whatever, you can think, oh, that sounds like the binomial distribution. So we've got n equals 3, and the probability of a size fault is 0.15. So just using, and we want to have exactly 2. So when we're doing it on the calculator, you just choose this time, and we haven't done this one for a while, just PDF. Okay, so X is equal to 2, the number of trials is 3, and the probability of success is 0.15. All right, so there you go, 0.057375. Try to just do it 4 decimal places. You can see the notation there for the binomial distribution, so you can either write that or just 3, 2, doesn't matter. All right, question D, a particular box of 25 rods has 4 rods in it which have size faults. A sample of 3 rods is withdrawn without replacement. Find the probability correct to 3 decimal places that a sample contains 2 rods with a fault. All right, so you can see with that tree diagram all the different combinations you can have. So I really like tree diagrams. I think it's a great visual way of seeing what's happening, but you need to understand what we're drawing here. So we've got a particular box of 25 rods, has 4 rods in it which have size faults. Okay, so that's where the 4 out of 25 has come from. A sample of 3 rods is withdrawn, so that means we do the tree diagram 3 times without replacement. So each time your number of rods, in this case, decreases by 1. Find the probability correct to 3 decimal places that the sample contains 2 rods with a size fault. Okay, so if you think of F being the fault and F dash being the not fault, and that one is missed a dash. If we're going along the first row, that means all 3 have a fault. Then we've got 2 without. Okay, so oh no, there we go, it's all right. So 2 fault and 1 without a fault. So that's where the probabilities have come from. So this one is 4 over 25, then this is 3 over 24. So we've taken 1 rod out with a fault, so that's why it's dropped down to 3, and then also we decrease the number of rods, and then 21 over 3 for this one. So 21 over 23. Now, you can go ahead and do the probabilities. You don't have to do it for all branches, but you will realize that you do end up with the same. All right, so that's why it's just 3 times that, and he's put a little asterisk next to the ones that have the fault, although I think he should have put an asterisk next to this one, but it doesn't make any difference. All right, so when you're going along your branches, you multiply, and because we've got 3 of the same thing, you multiply it by 3. Okay, and I think that might be it. Yay. All right, girls, long video, I know, but hopefully that's been helpful. Bye.